number 91. Woo! Who loves related rates? Anyone? Okay. All right. So, listen. Related rates. When you realize you have related rates, they're always an issue of you're taking the derivative with respect to time. Now, I often tell people the first thing you should look at are what are all the rates with respect to time that they give you and they ask you for. Read the problem, look at it. I'm looking for with respect to time rates. I notice cubic feet per minute. There's a rate with respect to time. What is it for? And if it says cubic feet, I think we've got that. That's volume. So write that down. dV dt. Also take into account whether it is growing or shrinking. You have to decide if this rate of change is a positive or a negative number by reading the problem carefully. So when you read the rest of this volume statement, if water flows into the container at a constant rate, so then dV dt being V being the volume of water in the container, this is a positive rate of change. Now, I don't see any other rate of change numbers, but do read it carefully. Then I'm trying to find what rate of change do they want me to figure out. So I noticed the words how fast is, there it is. How fast is the water level rising when blah, 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 okay? What matters? This is asking you for rate of change of the water level. Water level is going to be whatever letter you want to give, probably H for height, because that's what that H in this volume formula represents. So we want to find dH dt. I like to put equals question mark, but everyone does things how it makes sense to them. Now, I am not given any other rates of change. When I look at all the other numbers, because these are things you have to do. You have to sit here and look at every single one of the numbers. I'm changing my highlight color. I'm looking at all the numbers. I've got a 4 feet. I've got a 12 feet. I've got a 5 feet. These are all just lengths. They are not rates of change. Now, when I go to the picture, I see the 4 feet and the 12 feet in the diagram. The 5 feet is a when information. And I warn you, when information, never plug that in until your very last step. So you're looking at, you need dV dt and dH dt. That's what you need an equation for. Now your step is, what is the formula that brings V and H together? Now they gave you this formula for volume, but the variables in there are V, R, and H. Do you have rates of change being given or asked for all three of them? No. So pay attention. I see the wandering. I know, it's hard to pay attention. So R is a problem. I don't have its rate of change. Now, I could take the derivative with respect to time with the R in there and the H in there, but I'm going to have to go through a product rule. And then I'm going to have to figure out a relationship that R has with the other variables and bring in a whole new rate of change if I don't take care of this first. I don't want to take the derivative with respect to more variables than I actually am dealing with in the rates. I will save myself a boatload of time if I take a moment to identify that I only am able to deal with V and H once I take that derivative with respect to time. I don't know dRdt. So I have to figure out either what is the relationship that R has with the other variables, or do I actually have a constant R? So the answer to that second question, do I actually have a constant R? No, I don't. It's a cone. As the height is changing, as the volume changes, as water flows in, that radius is growing. So I have to figure out what is the relationship of R with other variables. And then take a moment to think about what seemed like extra information. The 4 and the 12 may have seemed like extra information, but that provided you with a ratio, because they expect you to be aware of the geometry of similar. And that is that if you have, shall we say, a cone within a cone, they are similar. If you have a cone within a cone, do you see what I'm saying? This is my water. Ooh, let me use a thicker pen for, ooh, look at that, that's water. And the water inside that cone creates its own cone that is similar to the original. When shapes are similar, their ratios, their one-dimensional ratios, have the same ratio. So what that means is if I compare in my, I'm just going to draw it over here so I can clearly show that this is R and this is H. My R to H ratio of my water cone must be equal to my R to H ratio of the larger cone. And now I need to isolate R in terms of H. 4/12 is 1/3, so R is 1/3 H. Before I take any derivative with respect to time, I want to change into having only 2 variables and not 3. So I'm going to substitute in 1/3 H. Keep in mind I'm squaring it. By squaring it, I am going to create, and let me emphasize, I've got constant pi over 3, and then I have a 1/3 squared. So in total, I have 3 3's in a denominator. And then I have h squared times 1 more h gives me h cubed. So this is the simplification once I substitute into R that 1/3 h. And this is vital to do to save you time and allow you to actually get this finished. So now we take the derivative with respect to time. And if it's just plain old V, then dv dt. On the other side, I have constant multiple. And then when I do chain rule, which I'm always doing implicit differentiation, is chain rule. H is my baby function because it's not time. So derivative of blah cubed is 3 blah squared. The chain rule says give mommy her baby and multiply by the derivative of the baby with respect to dun, 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 time. Once that is laid out, all you have left is, quote, plug and chug. So you're looking for dv dt is known to be positive 6. I need to find dh dt. And then that when information, when the height of the water is 5 feet. And then it's time to throw that in your calculator. And can someone tell me which of these was the answer, or I can go check real quick, but your calculator is going to give you the answer at that point. D, thank you. And that was 91.